When you ask a diffusion image generator to make an image, it begins with a grid of random numbers. How can those numbers become a clear image that follows your request? The same model examines the grid many times, and after each examination, the program changes the numbers to remove some of the predicted noise. After many changes, those numbers form the final image. To understand why this works, we must first see how the model learns to predict noise when the correct answer is known. The correct answer is known because the program creates the noisy image itself. It starts with a real clothing image from Fashion-MNIST, creates random values of the same size, and chooses how much of the image and the random values to combine. Let's follow two matching pixel positions. The clean image has normalized values 0.8 and -0.4, and the noise grid has values 0.5 and -1 at the same positions. After applying the chosen amounts, the image part becomes 0.64 and -0.32, while the random part becomes 0.3 and -0.6. Adding these parts gives 0.94 and -0.92, and the same calculation applies to every value in the image. We can now give the three grids short names. The clean image is x0, the added noise is epsilon, and the noisy image at level t is x sub t. Since the program created epsilon, it knows exactly what the model must predict. It can also create x sub t at any chosen noise level with one calculation, so it does not need to pass through every earlier level. This process is called forward diffusion. Each training example gives the model a noisy image, its noise level, and the exact noise that was added. The model can therefore learn from every noise level. However, when the noise is strong, many different clean images can produce almost the same noisy image. We now need to determine which noise value the model should predict in that case. When several clean images can produce almost the same noisy image, the model cannot determine which clean image produced it. During training, these similar noisy images can have different correct noise values. Training measures the squared difference between each prediction and the correct value. So the prediction with the smallest average error is the average of those correct noise values. The same formula can turn this noise prediction into an arrow that shows how the current noisy image should change. Repeat this calculation for many possible noisy images, and the arrows form a field. Each arrow points toward nearby image values that occur more often in the training data. Each arrow is called a score, and all the arrows at one noise level form the score field. The score does not select a complete clean image. It gives only the direction of the next small change. This field depends on the noise level. With strong noise, the image values are spread across a wide area, so the arrows change gradually. With less noise, the values gather near the clean images, so the arrows can change quickly from one point to the next. The model receives the current noise level with the noisy image, so the same model can learn a different field for each level. One arrow supplies only one small change. After that change, the program asks the model for a new arrow at the next noise level. This repeated update process is called sampling. Sampling starts when a seed is used to create the first grid of random numbers, and the same seed lets the program create that starting grid again without storing an image. At the current noise level, the trained model examines the grid and predicts the noise that was added. A separate calculation uses this prediction, the current grid, and the next noise level to produce the next grid, and this calculation is called the sampler. On screen, the white arrow shows the direction obtained from the model prediction, while the orange arrow shows the actual change made by the sampler, so the two arrows represent different values. After each change, the noise level decreases, and the same model examines the new grid. Repeating these steps turns the starting random values into an image. If we repeat the process with many starting grids, the resulting images follow the patterns that the model learned during training. Different samplers can use the same trained model because they change only how its prediction is applied. Some use more steps or larger changes, while some add new random values during the process. Others add no new random values after the starting grid is created. These choices can produce different paths and final images without changing the trained model. This explains the repeated changes from noise toward an image, but one visible pattern still needs an explanation. Broad shapes usually become stable before small details. Broad shapes usually become stable before small details because natural images do not contain the same amount of change at every level of detail. Changes that extend across many nearby pixels are usually stronger than rapid changes between neighboring pixels. Random noise has about the same expected strength at every level. When the noise is strong, broad changes are therefore easier for the model to detect, while fine edges and textures remain hidden by the noise. Broad changes are called low spatial frequencies, and fine changes are called high spatial frequencies. An image feature is easier to recover when its strength is large compared with the noise. This comparison is called the signal-to-noise ratio. At first, this ratio is usually higher for low spatial frequencies. As the noise decreases, the ratio improves at high spatial frequencies, so fine details become easier to predict. This is a common pattern in natural images, not a fixed rule, and a later update can still change a broad shape. So far, the updates have been shown on image pixels. Modern generators usually apply them to a smaller grid of learned values instead, and the text request changes each prediction made on that grid. The smaller grid reduces the amount of work. A color image with 3 grids of 512 by 512 pixels contains 48 times more values than 4 grids of 64 by 64 values. Classic Stable Diffusion uses a trained part to make this smaller grid. This part is called the image encoder, and the smaller result is called the latent. The 4 latent grids do not represent red, green, and blue. They contain learned values that preserve the information needed by a second trained part, called the image decoder, to rebuild the image. During training, the encoder converts each clean image into a latent before noise is added. During image generation, the encoder is not needed because the process starts with random values that already have the latent shape. All repeated noise predictions and changes occur in this smaller grid. After the final change, the decoder converts the latent into pixels once. Text must therefore change the noise predictions before this final conversion. The program divides the text request into pieces and converts each piece into a list of numbers. These pieces are called tokens, and the part that converts them is called the text encoder. Inside the image model, the image information at each location is compared with all the text lists. The model gives more weight to text pieces that are useful at that location and combines their information. This operation is called cross-attention. The weights are calculated again each time the model runs, so a word does not remain connected to one fixed image area. Instead, the complete text request changes each noise prediction. The strength of this text effect can also be controlled. Run the same model on the same noisy latent and noise level 2 times. Without the text request, the prediction is 0.4 and 0.1. With the text request, it is 0.7 and 0.5. Their difference is 0.3 and 0.4, which is the change produced by the text. Multiply this difference by 3 and add it to the prediction without text. The result is 1.3 and 1.3, so the text effect is now 3 times as large. This operation is called Classifier-Free Guidance. During training, the text is omitted from some examples, so the same model learns to make predictions both with and without text. It does not need a separate model to judge whether the image matches the text. A larger guidance value can make the result follow the text more strongly, but it can also reduce variety and produce excessive colors or repeated shapes. The familiar controls now have precise roles. The seed creates the starting latent, the step count sets how many changes occur, the sampler calculates each change, and the guidance value controls how strongly the text changes each prediction. The complete process can now be followed from the first random value to the final pixel. During training, the program adds known noise to real images and teaches one model to predict that noise at every level. During generation, the seed creates the starting grid of random values, the model predicts the added noise, the text request changes that prediction, and the sampler calculates the next grid. The step count determines how many times this repeats, and the guidance value controls how strongly the text changes each prediction. All these changes occur in the smaller grid, and the decoder converts the final grid into pixels once. The image is not hidden in the starting noise. It develops because each prediction uses patterns learned from real images and information from the text request,